In our next example, we're going to look at a function that we've seen before, the Dirichlet function, defined here. D, let me say, d of x is equal to 1 if x happens to be a rational number, and it's 0 for all of the rest. In other words, for the irrational numbers. And the question is, does the limit as x goes to x naught of the Dirichlet function exist for any x naught? For 0 or for 1 or for a half or for pi? And we'll find out that no, it does not. That limit does not exist. Essentially, I'm going to do a proof, and I could have done a proof by using the negation of the definition of what it means for a limit to exist. But I'm just going to, this might look a little bit like a proof by contradiction. But notice, before we start, every x0, every number is an accumulation point of the real numbers. So it's a valid question here. And this is my graph if you can't see it very well. This is the, let's see, zeros. This is all the irrational numbers that I've plotted, in theory. This would be the x-axis. And at x equals 1, I plotted f of all of the rational numbers here. So in particular, f of 1, f of 2, f of 3, those would all have a height of 1, since they're rational numbers. Okay, let's just suppose that the limit exists and that it's equal to L. I'm not even going to choose I'm just choosing a randomly selected x naught. Suppose that's the case. All right? If that's true, we will show, using the definition, that for every epsilon greater than 0, I am going to change it. I'm going to show that there exists an epsilon greater than 0. So we are going to use the negation of the definition of what it means to have a limit at x naught. If it were the case that the limit existed, we would say for every epsilon there exists a delta. Well, I'm going to find an epsilon such that for every delta greater than 0, and the remainder of the definition then we would have to negate. We will show that. All right, I'm going to have to squeeze it in here. I'd like to get it all on this line if I can. So this is essentially just the negation of what it means for a limit to exist at x naught. So there exists an epsilon such that for every epsilon, this is going to hold true. We find an x that's very close to x naught, yet d of x is greater than or equal to epsilon away from that proposed limit, capital L. And just for terminology, I'll write down what I put in my notes. And just another way of writing this. There exists an x in x naught minus delta to x naught plus delta. And then I have to put minus x naught, different from x naught. And then I'll just put the same thing up here. D of x minus L is greater than or equal to epsilon. These two are just two ways of writing the same thing. This right here means this. And notice I didn't have to say x is in capital D because our capital D is all, the domain is all real numbers. Okay, let's let epsilon equal 1/2. There exists an epsilon. I'm choosing epsilon equal to 1/2. And perhaps not necessarily a requirement of the proof, I'm going to put a little statement in here to clarify something that we saw in the last chapter. And recall that the distance between L and 0 is greater than 1/2, or the distance between L and 1 is greater than 1/2. I guess I should put greater than or equal to 1/2. For all possible values of L. Again, remember what that's saying? Every real number is at least 1/2 away from 0 or from 1. And we'll use that in just a minute. For all delta greater than 0, x naught minus delta to x naught plus delta, that's an interval on the real line, contains infinitely many elements from both Q, the set of rationals, and from R minus Q, the set of irrationals. And again, this is R minus Q right here. If x is not in Q, then it's in R minus Q. Okay, can anybody see where we're going here? The fact that there are infinitely many elements, I don't care about. I just want one from each of those sets. So I'm going to let little a be an element of the rationals inside this interval. So I'm just going to intersect the rationals with that interval. And unfortunately, I need to put brackets around that and say minus x naught. I know it looks complicated, but it's not that bad. It's just saying let a be some rational number in the interval, the neighborhood around x naught, but that's different from x naught. So a is not equal to x naught. And little b is going to be an element of almost the same looking thing, except I'm not going to put rationals there. I'm going to put R minus Q, the irrationals. Well, I put little question marks up here to fill in, which is really simple. Oops, this function is not f, it's capital D. Okay, so again, we chose a to be a rational number in this interval that's different from x naught. That means since it's rational, that d of a is equal to 1. We chose b to be an irrational number in this interval, so we intersected those two, different from x naught. So d evaluated at b gives us a 0. So we can finish this up by just saying, therefore, we found two neighbors, two values a and b in the neighborhood of x naught that are different from x naught, but we've got therefore either d of a minus L which is what? D of A is 1 minus L, is greater than or equal to epsilon, which is 1/2. Or the other one is D of B minus L, which is 0 minus L, is greater than or equal to epsilon, which is 1/2. And that's kind of a contradiction. So when we assume that this was true, it's not true, it's false. And again, this down here is just using the fact that this is the distance between L and the number 1. This is the distance between L and the number 0. One of them has to be bigger than or equal to 1/2. And we chose our epsilon to be 1/2, and that's where we get our contradiction. I'm going to call this method of showing the problem method number 1. And I'm going to show it again using a method number 2.